I don't even go that. I usually just from the graph. It's something I can throw in the oven easily.
See, like I like that, but like I get sick of frozen stuff.
I do too, but I can't cook.
So who we are and what are we doing? Huh? Yeah, that's good. But we are postponing predicting the future for a little bit, right? You'll predict the future next Friday, when you'll show all advanced computational techniques to predict the future. And which of them, which of the models, and tech support, can you please project the thing? Okay. We are browsing in space of ideas, models, and techniques, trying different skills of quantum mechanics that everything targets to predict outcome of measurement from the instrument, right? That's fine, you can show the class there. I see keen interest immediately. So which model are you working on right now?
Ladder operators.
Huh?
Ladder operators.
Ladder operator is like a tool, is an instrument. But what is the model to which we apply this mathematical technique?
Harmonic oscillators.
Yes, and harmonic oscillator is also mathematical abstraction. What does it correspond in a real world? Examples? Huh?
A wave.
Well, wave is like continuous. Many oscillators can form a wave, but something simpler. What kind of oscillator?
The inflatable waving arm dudes.
Huh?
Inflatable waving arm dudes.
But something related to your future degree.
Oh, you mean chemical bonds?
Huh?
Chemical bonds.
Yes, yes. So we are looking at chemical bonds near the equilibrium. Yeah. Okay, thank you. I'll do the rest. And why are we doing so simple models instead of doing something more attractive? What is the problem? Why we are looking on like particle in the box and oscillator rather than immediately going to, say, molecule of coffee?
Way too hard.
Yes. And which? Wrong slide. So here we are in the class. Here is our old, here our lab that we completed. There will be one more lab before presentations. So in the lab we covered the first column, and on the coming Wednesday we will be covering observable visualization. No one signed up for movies, but it will be either Michael or Isaiah. And you do have a homework, which I decided it will be unfair to modify the homework, but it is fair to modify the extra credit. So there will be, similar to last meeting, there will be two mathematical procedures, one derivative and one integral, as you can guess. But the integral is so complicated that I cannot do it. Well, I can do it, but not in the limited time. So the part of today's lecture will be your extra credit thing if you are interested in. So we are browsing in, right now, we all are much richer in a sense of possessing many methods for physical chemistry and quantum theory than in applications, because they are so complicated. So we already went through free space, electron in free space, particle in the box, and harmonic oscillator. And we are going to practice several techniques, but right now, before we go forward, we need. Thank you. We do need to solve time-independent linear equation, and I was promising it, and no one was objecting against the idea to take a shortcut, a discount, a sale. That instead of solving time-independent linear equation for harmonic oscillator, we applied so-called technique of
Ladder operator.
which are
Operators that raise and lower like the excited state of an electron.
yeah. So you browse between eigenstates of the solution if you know them, and right now we do not know them, but we already apply them as a tool to find them. So if the states are available and there is a ground state below which there is nothing, raising operator goes from ground to first excited, second excited, and lowering gets down. But if one applies lowering operator to the lowest state, one is getting what?
0.
Nothing. And this is an equation that we have solved and obtained which function? Ground state wave function, which mathematically looks as a family name from German money. Gaussian, yeah, Gaussian distribution. And then at the end of, not at the end, at the beginning of last meeting, we practiced integration in order to find normalization. What is your guess? What are we going to do today? Just project our train of thoughts. What would you do today? I know the best way is just to stand up and live and have some relaxation. But if you would set up a goals of the course to predict future, predict observables, focus on oscillator, already knowing ground and first excited state,
Normalize the states.
normalize the states, and if you have like zeros and first, would it be reasonable to go to second? Yes. Simple logic, right? And we are going to apply the raising operator again, now to the state number 1. So here is an equation that we all are assumed to memorize, but I'm hesitant to request it from you because I have problems memorizing things myself. But those are raising and lowering operators which are superposition of position and momentum. And today I frivolously replaced variable r to variable x, just because editing it through all nodes will be too long. And momentum has imaginary factor, and position has this mass times frequency. With overall, there is an overall dimensionality factor going out of the brackets, and these operators raising and lowering, they are dimensionless. So these factors are made in order to make dimensionless position and dimensionless momentum and then add them together. So what was the main outcome? Well, there were two outcomes of last lecture, and I know everyone hates to remember. Therefore, I'm making a review session. One outcome that you have gloriously normalized ground state wave function, and another one that we together have found the first excited state. How did it look like? Can you hand wave to show what was it? I can show, I can hand wave for the ground state. Can you hand wave for the first excited? Perfect. Ah, I should put camera. Can you show it once again? Excellent. Thank you. Let's see if recording 2 is successful. You will see us. So Ben will show this shape, right? And do you have any expectations? Well, I know this all is boring and irritating to some extent, but if you would focus on the subject and try to project train of thought and from your previous experience in the course, what would you expect from second, third, fourth excited states? In the same sense as Ben showed, like first excited. How the second excited should look like? Huh?
Something like that, or maybe the other way.
So how many?
Like two times rho s is 0.
It is not shown here, but can you show once again?
Oh gosh, okay.
Yes. So how many times should it cross this 0? Twice. If it will be third state, 3 times.
Yeah.
Four states.
4 times.
Oh, 2.
3.
Yes,
I don't know, right?
excellent. So you are ahead of the whole class by 3 meetings. It's very hard math to get it, but you already got it intuitively, right? So why the number of intersections with x-axis grows as we go to higher excited state? How to interpret it? This was correct, and we will show it sooner or later. Or just this figure is often reproduced in all textbooks. But
Yes, and you're multiplying by the function by another higher power of x.
yes, it is a very mathematical answer. It's correct. But if we interpret it like natural scientists, physicists and chemists,
because like this, because when you like square the wave function in order to get the probability curve, like it's like they're in like segments, and so it's going to have like increasing number of peaks in probability, and it's going to be more spread out.
okay, this is the same trend as we have seen in particular in the box, but wide number of these peaks grows with number of excited state.
More potential orbitals to fill, and doesn't each peak kind of represent? Okay, never mind.
No, it's interesting, but there are no orbitals. Our eigenstates are orbitals. It's typically chemists speak about orbitals about like atomic orbitals, right? But here we do not have electron. Right now we are quantizing nuclear motion. But just nuclear motion, interatomic bond. And it was absolutely correct that the higher the excited state, more fringes are. What does it mean, higher excited state?
More energy in the electron.
Yes. Energy consists of which 2 parts?
Potential and kinetic.
Yes. And kinetic, so both increase. If you have higher kinetic energy, what else increases? Kinetic energy is square of what? Huh?
Velocity.
Yes. So the higher excited state, the higher the, yes, or momentum if you want to look smart. So the higher excited state, the larger momentum. And do you remember from the free electron in the free space? If you increase momentum, how does plane wave change?
Spreads out.
Huh?
Spreads out.
Well, it not wave packet, but eigenstates. A plane wave, infinite. E to the power ikx, where k is by factor h bar is the same as momentum.
Doesn't it just get more fringes?
Perfect. You guys should team teach this course. So By collective effort, we deduce that the higher the excited state, the larger the momentum, velocity. And when the momentum is higher, wave function experiences more frequent fringes, more frequent oscillations, right? Then if instead of continuous free space, we are looking on the confined harmonic oscillator, instead of plane wave, it will be eigenstate with larger number of fringes. So the higher the momentum, the larger the number of fringes, the denser fringes are. Okay? So you already, by now, I need to complete just some boring stuff of wrapping up these ideas into math language, but you already have the intuitive picture of solution of time-dimensional equation. What are the eigenstates? There is one more piece of new information that you may never looked at, but I hope to surprise you. And the following thing will make life easier. Maybe not for all humankind, but those who are dedicated towards quantum course or some quantum calculations. You already suffered integration of Gaussian function, which is not very complicated, but it takes time. Right? And we kind of plan that upon we find an eigenstate, we may want to make sure that it is normalized. Okay? So why normalization is needed?
Oh, so that when you try and find the expectation values, the wave functions will cancel out because they're normal?
Yes. In order to be correct in the obtaining expectation values, observables. Yes. So eigenstates must be normalized. And if you have found eigenstate, it is it doesn't hurt. Well, it does hurt, but it is needed to check that each wave function gives 1 upon taking its square and then integrating from plus to minus infinity, right? So one hypothesis that we started to believe, and we were right in this, that applying raising operator subsequent to ground state, then to first state, to second state, one can ramp up and get all excited states, equivalent to solving Schrödinger equation. But we didn't know, will it give us right normalization? So the answer is that normalization of all of the excited states and result of application of raising operator, creation and raising whatever, ladder up operator, differ by specific factor. And to some extent it will be the main outcome of today's meeting, if everything will go successfully. If you apply raising operator to ground state, you'll get first excited state multiplied by square root of 1, which means normalization factor, which was for a ground state, will stay the same for first excited. If then you take first excited, apply raising operator once again, you'll get true, correct second excited state multiplied by factor square root of 2. So if we if you find this function and then normalize it, we will discover that one needs to multiply it by square root of 2 in order to have it normalized. We will never go further in true mathematical derivations because it gets harder and harder. But if you would go further and apply raising operator to second excited state, we will find that if you generate true eigenstate, but in order to have it normalized, one needs to multiply by square root of 3. And then if one keeps on with this progression, applying a raising operator to eigenstate number n will give you eigenstate number n plus 1 multiplied by square root of n plus 1. How does, so it is a specific question for mine. You need to derive equation for all of us in your head without pencil and paper. How does the number of the wave function crosses the x-axis corresponds to the number of orbital, number of eigenstate?
Then just the same, because
Yes, perfect. Yes, everyone follows it. So for ground state, it doesn't cross. For first state, it crosses once. For second state, it crosses twice. Right? So number of times it crosses the x-axis goes as a factor in front of here. Okay. Well, basically we are done. But I need to work for salary. I'm getting to mumble, so I invite you to follow me if you have energy. But basically, you've got main idea. This is what was main message of today's meeting. Okay. Or doing something heavy of you looking forward, you can dim the light, take popcorn and fall asleep. So actual content of the lecture is more boring details. The life is already hard on us, especially on me when if I need to write everything. In previous years, I was just handwriting instead of showing slides. And if you need to repeat this m omega divided by h bar, your hand is tired. So why don't we rename this factor as single symbol? Otherwise, it will be too complicated because the equations will get longer and longer. So by applying raising operator to the first excited state, which was like linear function times Gaussian, as Michael showed. No, Michael was showing the higher order. This was shown by Ben. Right? So if we apply raising operator to the first excited state, we are getting again Gaussian factor times second order polynomial. So I want to have two results of today's meeting. First result, just practice raising operator to this function and get this polynomial. Second part, take it, square, integrate, and see if it will be equal 1, normalize it. So if we would normalize it, we would find out that one needs to have this factor 1 over square root of 2 in order to have the function normalized. And then, as a result, we see that applying of the raising operator to the first excited state is the second excited state multiplied by square root of 2. If you want to get second excited state, you need to apply raising first, divide by square root of 2. And then we project this observation to higher order terms. But we are not going to derive it. We, looking on this equation, we project this to the general. So, two goals. I would be so happy if time runs out. Now I need to perform for 20 minutes, 21. So, application of raising operator, which will include multiplying by independent variable and taking derivative, and then integration of this function square. I promise to complete first part, and I promise not to complete the second part, because it's a lot of writing, and therefore part of this integral is delegated as an extra credit to your homework. So, beginning the lecture. Yes?
So the extra credit part is integrating that function after we square and everything.
Yes.
Okay.
So this was first excited state with undetermined normalization factor, linear times exponential, and the raising operator includes position and momentum with certain factors. So we are trying to replace m omega over h bar onto this new constant everywhere where it is possible to shorten the time we spend for writing. I'm supposed to write it over myself. Otherwise, it will be there is a big danger to. I close eyes, show the slides. You close the eyes and sit there. I'll try. So. It should be square root of everything we remember. Mass, frequency, h bar. Here it should be mass and frequency x minus I d. And momentum is minus I h bar dx, right? No one objects. So we plug this in, and then we are getting minus h ddx. So minus because there were one minus inherited from definition, one minus from definition of momentum, and the third minus from imaginary unit multiplied by imaginary unit. So 3 minuses give minus. So if we take Planck constant out of brackets, we need to divide everything by Planck constant here and remove Planck constant there. And we have, Planck constant itself, it can be Planck constant square and then square root. Right, square root, 2, and omega h bar. So we can cancel second power in the numerator and first power in the denominator. Then we have this a dagger equals 1 over 3, and then here square root of h bar over m omega will be same as square root of 1 over alpha. Then in the brackets, we will have alpha. So this m omega divided by h bar is alpha times x minus d dx. Okay, good. So we did nothing. It is same raising operator, just it is more comfortable to practice application of this operator to the first eigenstate. And since we are going to normalize anyway, we can forget about the factors temporarily and just apply this alpha x minus ddx to the first excited state, right? Which was linear function times Gaussian function. A couple of meetings ago, we derived that there should be 1/2. So we need to practice this expression, which will be multiplication taking derivative of a product. So the first term will be just alpha x squared e minus alpha x squared over 2. And then there will be two terms here inherited from applying derivative over position to product function, right? So, and it will be minus sign in front, minus applying derivative to x, ddx, which will be 1 times e minus alpha x squared divided by 2 plus x unchanged, and then we practice derivative to the Gaussian function. Which will be minus alpha by 2 times 2x, right? The derivative of exponential is exponential itself. And derivative of the power. So constant doesn't get changed, and derivative of x squared will be 2x, right? And then factor 2 cancels. And we are coming to the interesting observation. What is the power of this polynomial? In which power x comes up? Square. In which power x comes here?
Square.
What is the factor in front of it?
Alpha.
So it will either cancel or add it together. Is it cancelled or added together? What do you think?
Added.
Added together, because one minus here and another minus here. So it will be 2 alpha x squared. Then we have this minus 1, and we put exponential outside of a bracket. Alpha 2 x squared. And of course, there should be normalization factor, but we'll take care of it later. What should we do if an unknown function is introduced to us and we really want to get acquainted with it? Based on today's review session, Ben and Michael know very well what to do with the function. To represent it by hand waving, or better to draw it, right? And you already know what this function should look like, right? So it should cross x-axis in 2 points. Up, down, up, down. But we may want to just double check that it is this way. So it's phi 2, some factor n2 is this function. Alpha x squared minus 1. What is, if you want to draw just this 2 alpha x squared minus 1, how the function look like?
It's an exponential that's shifted.
Not exponential, quadratic.
A quadratic
Parabola.
that is shifted down 1 from the origin, but has 2 times the, or the skin slightly skinnier because it increases a lot faster.
So minus 1, right? Just shift it down. The exponential is something that we loved from childhood. Not exponential, the Gaussian function. And now we need to multiply these two functions and get the result. So upper function was plus, minus, plus. Upper function is plus everywhere. And there will be 2 zeros. So it will be 0 at how does this point relate to value of alpha? We can quickly check it. 2 alpha x squared equals 1. X squared equals 1 divided by 2 alpha. X equals plus minus square root of 1 over 2 alpha. So this minus square root of 1 over 2 alpha. This is plus 1 over square root of 2 alpha. And then the resulting function plus times plus will be plus, and it should be zeros at the infinity, asymptotic. So it's plus 0, 0, and in the middle should be minus. Right? Supporting the scientific intuitive hypothesis by Michael. And you know how to interpret it, right? The higher the index of eigenstate, the higher the energy, the larger the velocity, the larger number of fringes. Okay, glorious 8 minutes for most complicated part. Done. And now we need to normalize. We need to normalize this function. I skipped it from discussion, but the energies of ground first, second states will be proportional to h bar omega and goes as progression 1/2, 3/2, 5/2. So they will be offset by equal amount of energies. Okay. Normalization. So our secondary function is unknown normalization constant times 2 alpha x squared minus 1 minus alpha over 2 x squared. Normalization is phi star 2 phi 2 dx must be equal 1. So it will be n2 squared 2 alpha x squared minus 1 squared e to the power minus alpha x squared. So by taking exponent square, we just increase, multiply the power by 2. So removing this 1 over 2 factor. And then all this expression needs to be integrate, right? Good extra credit work. Worth of a big credit. So, if this is A and this is B, we can just open, no, just open the bracket. And the goal of this exercise is to solve for n, for normalization factor. Everything else should reduce to like square root of pi, square root of alpha. So square integral 4 alpha square x to the power 4 minus 2 times 2 to the power 4 alpha x squared plus 1 multiplied by e minus alpha x squared dx. Right? So how are we going to take this integral? I'm not going to take this here. I will just show guidelines and take declare the result. So you see that there are 3 terms. So we can open brackets and consider this expression as 3 independent integrals. Why?
Because there's summation.
Distribute it out and then.
Yeah, because if you look online for table of integrals, some of them can be already there. And there is no requirement to derive all this boring stuff. If you can find online, that's fine. Just show the origin. It's PChem. It's not. It is not calculus. But some people hate internet. Some people hate tables of integrals. Therefore, one can take it by pen and paper. And by the way, if we look on the last term, it will be just integral of e to the minus alpha x squared dx, right? It's a Gaussian integral that should be like square root of pi, if we take care of this alpha factor. So we can divide and conquer, same as ancient Romans. And we also need to take care of this alpha factor.
Is it alpha over 2 or just alpha?
You can answer yourself.
Oh, it's squared, though.
Right? So wave function was over 2, but when you do normalization, it will be without doing bigger. Okay, so taking care of the alpha. What if we assume that it was a new variable, so that we get just pure e to the power minus some variable squared. So we just redefine variables that differ by square root of alpha. And then our original variable is replaced by new variable divided by this square root, and integration increment will also inherit this factor. 2 minutes more. So if you will look on the last integral, right, e to the minus xi squared, dxi divided by the square root of alpha, and we already know that integral of Gaussian function without any factors will be square root of pi. So the last term in the integration will be square root of pi divided by square root of alpha. But there are 2 more integrals. So it is the stuff that we need to take, already cast in terms of this xi variable, right? And we need to solve it for n2. So there, inside the brackets, you have xi in the power 0, power 2, power 4. So one can introduce notations. So it will be integral 0, integral 2, integral 4. And integral 0 will be just square root of pi. Then, as a hint, if you just explore integral 1 when it is in the first power, one will recognize that it makes life easier. This one can be taken, less than one line. And then, knowing this integral, one can probably practice by parts integration for other stuff. So then, taking these three things, plugging in, and solving for N2, for normalization factor. If you do it carefully, the right answer will be here. 1 square root of 2, this combination of factors, and then the polynomials that we know about. There's an error. There should be number 7. Have a nice weekend. I would be happy to answer emails about homeworks or lab. But wishing you accumulate a lot of strengths towards next week.
Definitely got bored in like an hour.
Got what?
Bored. Like, this is actual research work, not bad. I work too, but it's in 5 hours. Mine's at 1, but like, I don't know if I'm gonna be there, but it's like, I'm gonna show up and then I'm just gonna do stuff on my own. I'm probably listen to podcasts the whole time. It's nice. Just make a bunch of forms.